Hello, I'm Norman Wellberger. Today we're carrying on from the last lecture where we introduced the basic laws of elliptic trigonometry, which turned out, rather surprisingly, to be the same as the basic laws of universal hyperbolic geometry. So we have a unification of hyperbolic geometry and elliptic, or closely related, spherical geometry, in terms of the main laws of trigonometry that cover both of them. Today's lecture we're going to prove these laws. These are going to be somewhat novel proofs. So this is a sort of a publication of a kind. And so I'll say just a few words about that. It's kind of a novel idea of publishing results on YouTube. So if you want to refer to such results, I think the standard format would be name of author, say me, and then name of title, UHG 42, Trigonometry and Elliptic Geometry 1 or 2. And then the publisher is YouTube, and then the URL for the video, and the publication date. There we can refer to that just as easily as we can to a published paper. Okay, so what we're going to do, we're going to start with just a quick review of the format, the framework that we've established in the last lecture, and then we're going to go on and find very nice, elegant proofs of these very important formulas. Okay, so we're interested in three-dimensional geometry. We've got two projective points, which are just lines through the origin, say A1 and A2, determined by two vectors, say V1 and V2. And the main object of interest or measurement between these two things is the quadrants, or sometimes called projective quadrants, little q of A1, A2. It's defined by 1 minus the dot product of V1 with V2 all squared divided by the product of V1 dot V1, V2 dot V2. Which we could also write this way because V1 dot V1 is the standard affine quadrants, capital Q of V1. V2 dot V2 is Q of V2. All right, so this is a measurement of how far apart these projective points are. And now the main object of interest is three such projective points. So three lines through the origin forming an elliptic triangle, A1, A2, A3. And closely associated with that is the polar triangle, obtained by taking any two of the A lines, say A1 and A2, and looking at the unique line through the origin which is perpendicular to that plane. So that's A1 and that's A2, then this will be B3. All right? So B3 is perpendicular to A1 and A2, B2 is perpendicular to A1, A3, and B1 is perpendicular to A2, A3. So it gives us for every elliptic triangle another elliptic triangle called the polar. And now we define the six main objects of interest for this elliptic triangle. First of all, the quadrances, which are just the quadrances between the projective points themselves, Q1, Q2, and Q3. And then the spreads, capital S1, S2, and S3, which are defined to be the quadrances between the polar lines. So S1 is the quadrants between B2 and B3, and so on. Now in a picture, we might sometimes represent such an elliptic triangle by 3 points on a sphere. Actually a point together with its antipodal point, because when we're talking about elliptic geometry, the objects of interest are lines through the origin which intersect the sphere, the unit sphere, in a pair of antipodal points typically. So here's a way of visualizing 3 points in this setting, where each one of these represents the line through the center of the sphere, going also through these points. And where would the polar triangle be then? Well, you get these 3 points determine 3 lines, which are great circles on the sphere, and they're also planes through the origin in the three-dimensional space. And the normals to those planes are then the polar directions. So here's V2 and here's V3. So B1 would be the line which is normal to the plane formed by V2 and V3. So it would be a line in that direction there. Okay, and then this is the way we represent that on a diagram. So we would just sort of copy that part there and make it a little bit rounded to suggest that it's something spherical. And so there's A1, A2, A3. The quadrants is Q1, Q2, and Q3. And the spreads can be interpreted as how far apart these lines are on this elliptic triangle. Okay, so those are the 6 quantities of interest for an elliptic triangle. And our job is to prove the relations satisfied by these 6 quantities. All right, and here are the main laws. There's the spread law. S1 over Q1 equals S2 over Q2 equals S3 over Q3. There is the cross law, of which there are essentially 3 different versions. So this one is S1 Q2 Q3 minus Q1 minus Q2 minus Q3 plus 2, all of that squared equals 4 times 1 minus Q1, 1 minus Q2, 1 minus Q3. And the dual cross law is exactly the same, but with the Q's and the S's interchanged. And our job today is to prove these laws. And our main tool is going to be some elementary linear algebra, having to do with essentially 3 by 3 matrices. Here's the picture that we might keep in mind. So the 3 original lines in the directions V1, V2, and V3. And then the polar lines in the directions, say, W1, W2, and W3. So these 3 form the elliptic triangle A1, A2, A3 that we're primarily interested in. And here's the polar elliptic triangle B1, B2, B3. And our notation is that this W1 vector ought to be perpendicular to both V2 and V3. And similarly for the other ones. All right, so last time we introduced a little bit of a framework to discuss this kind of situation. We can represent the elliptic triangle by a matrix, just by recording the 3 vectors that span the projective points along the rows of a matrix called A. And then very usefully we can multiply A by its transpose, which gives us a whole bunch of dot products of various vectors with each other. So here is V1 dot V1, that'll be V1 times V1 column. And similarly, the other dot products formed by the 3 vectors. In an exactly analogous fashion, we can represent the polar triangle B1, B2, B3 by a matrix B whose rows are the 3 vectors W1, W2, and W3 in the directions of those lines. And we'll form the matrix W, which is B times B transpose, which is just the matrix of dot products of these 3 vectors with themselves. All possible dot products arranged in a sort of systematic way. And we'll introduce this very useful shorthand terminology. We'll write V sub ij to represent Vi dot Vj, which you can see is just the ijth entry of this matrix, capital V. And similarly, Wij will be the vector Wi dot with the Wj, which is just the ijth entry in this matrix W. So that means the ith row, the jth column, for example, the first row, second column, first row, second column, that would be W1 dot W2. So we would refer to this number as just W sub 1, 2. All right, so these matrices are very important. They're sometimes called Gram matrices. They encode all the inner product information in both of the elliptic triangles that we're interested in. Okay, so now a very important observation is that the relation of these 2 elliptic triangles being polars is really essentially the same as the following relation between the corresponding matrices A and B. So here's the matrix A, which has the vectors V1, V2, V3 as its rows. And here's the matrix B transpose, which has the vectors W1, W2, and W3 down the columns. In other words, the transposes of those vectors are down the columns. And what we know is that these are polar triangles so that V1 is perpendicular to W2 and W3, meaning that this matrix times either this matrix or this matrix is going to be 0. That's what the perpendicularity amounts to. So the polarity between these two elliptic triangles is essentially equivalent to the condition that the product of these two things is a matrix which has zeros off the diagonal. Okay, so we're going to assume that our elliptic triangle really is not in a plane. So these three vectors really span the space, so that both of these matrices are invertible. And then what we're going to do is we're going to renormalize our vectors. So we can renormalize, say, the vectors W1, W2, W3, just multiply them by scalars, which doesn't change the lines, to ensure that these diagonal entries are all 1. Okay? And after we've done that, then we get the relation that A times B transpose equals the identity matrix. Or, equivalently, that the inverse of A is actually B transpose. So this matrix relation captures the polarity of these two elliptic triangles. And it has an interesting consequence on the product of the associated Gram matrices. So if we look at V times W, and V was A times A transpose, and W was B times B transpose. Now when we look at that product, what do we find? Well, first of all, this is a matrix product, so associativity allows us to rewrite the order here as A times A transpose B times B transpose. All right, now A transpose B is the same as the transpose of B transpose A. I remind you that when you take the product of a transpose of two matrices, you get the transpose of the second one times the transpose of the first one. The order becomes interchanged. Now B transpose A, well, what is that? Well, here we know that A times B transpose is the identity, meaning these two matrices are inverses. And if they're inverses, then even if we multiply them in the opposite order, we'll still get the identity matrix. So this thing here is actually the identity matrix. And so that all disappears, and we just get A times B transpose, which again is the identity matrix from here. So as a consequence of this relation between A and B, we see that V and W are in fact inverse matrices without any transposes. Well, V and W are symmetric matrices, even though A and B are not. All right, so to summarize, here's the Gram matrix V, which is a symmetric matrix of just dot products of the V vectors. Here is the Gram matrix for the W vectors, W. And we've just established that, subject to the condition that these are polar triangles, these two matrices are inverse matrices. That's a key point that will drive our little proof. And so let me just restate what I've just said, that the Gram matrix W, here it is right here, is the inverse of the Gram matrix V. So the inverse of this matrix. Okay, so we know all about inverses of 3 by 3 matrices. How do you find the inverse of a 3 by 3 matrix like this? Well, the first thing that you need is the determinant. So the determinant of V, whatever it is, ends up in the denominator here. So there's a 1 over determinant V factor. And then what we have to do is we have to cook up a whole bunch of entries which are cofactors of this 3 by 3 matrix, suitably multiplied by plus and minus 1s. So what we're doing then is we're taking various rows and columns and eliminating them, and taking the 2 by 2 determinant of these sub-matrices that are left over. In fact, the only thing about that we really want to know is what are the diagonal elements of the inverse. Okay, well, I could write down what these elements are as well, but I'm not going to because they're irrelevant for us. The only thing we're really interested in is what are the diagonal elements of the inverse of this. And they're just simply this 2 by 2 determinant, v22 v33 minus v23 squared, and then the 2 by 2 determinant you get by eliminating that column and row. So v11 v33 minus v13 squared. And down here, this 2 by 2 determinant, v11 v22 minus v12 squared. If you're not that familiar with 3 by 3 matrices and their inverses, please have a look at my linear algebra series, LinAlg. Somewhere in the first half dozen videos or so, I talk about inverses of 3 by 3 matrices at some length and establish all these formulas. Okay, now we're ready to write down in a very explicit way what are the quadrances and spreads of our elliptic triangle A1, A2, A3. Okay, so what was Q1? I remind you that Q1 is the quadrants between V2 and V3. Okay, we had it in the form 1 minus V23 squared over V2 2 V33. But we can get that over a common denominator. So it's V22 V33 minus V23 squared over V22 V33. And you can perhaps see why that's useful. It connects to a determinant, which is an observation that we made in our last video. Similarly, Q2 can be written as essentially this entry here, divided by V11 V33, and Q3 is V11 V22 minus V12 squared over V11 V22. Now everything's completely symmetrical. So this being the inverse of this means that this is the inverse of this. So exactly the same formula will hold for the spreads, except that now we're talking about the quadrances between the W vectors, not the V vectors. So the spreads of this triangle are just the quadrances of the W triangle, so to speak. And we get that just by taking these formulas and replacing V's with W's. This determinant of V, let's give that a shorter name. Let's call it capital D. So that the determinant of W, which is the inverse matrix, will then necessarily be 1 over D, or D inverse. So this is great. We have explicit formulas for the 3 quadrances and the 3 spreads of our triangle in terms of these inner products, essentially, of vectors between the V's and between the W's. And so now we can actually have something very explicit to work with. And a little bit of algebra now is going to establish our 3 main laws. So let's rewrite those 6 quantities in a little bit more compact notation using the observation that those numerators that were in the previous expression were just really found by the entries of the diagonal on the inverse matrix. So that first numerator, which was, I remind you, V22 V33 minus V23 squared, that's the top left-hand corner of the W matrix times D. So if you look on that previous expression, you see that that little determinant is D times W11. So we get this more compact expression for Q1, an exactly analogous one for Q2 and Q3. And the ones for the spreads will be exactly the same, but with the roles of the V's and the W's interchanged. Instead of having a determinant of V up here, we'll have to have a determinant of W, which is D inverse. And now we can see that the spread law is obvious, because if you take S1 divided by Q1, what do you get? So if we take this expression and we divide by this expression, well, when you divide by a fraction, it's the same as multiplying by the reciprocal. So the V22 V33, which is in the denominator here, gets moved to the numerator of the result. And this W11 gets to go in the denominator below, giving us W11, W2, W33. And this D inverse that was here, and we'll combine with this 1 over this one to give us 1 over D squared here. So that's what you get when you evaluate S1 over Q1. And now you can see that this is completely symmetric in the indices. It's going to be exactly the same as what you get when you calculate S2 over Q2 or S3 over Q3. And that establishes the spread law, and in fact gives us a nice expression for what these quotients actually are in case we need it. In fact, it's nice to rewrite that as a corollary here. Let's have a look at S1 times Q2 times Q3. So if I multiply S1 by Q2 by Q3, what will happen? Well, there'll be a D inverse and a D cancels, and there'll still be one D left over. There'll be a V1, a W22, and a W33 in the numerator, and W22, W33, V1, V1, V33, and V1, V1, V22 in the denominator. So there'll be a bit of cancellation. This V11 will cancel with that V11, leaving V11, V22, V33 in the denominator, because these two guys cancel exactly with those two. So if you multiply S1 times Q2 times Q3, you get this expression. And that's the same as what you get when you take this thing and multiply everything by Q1 times Q2 times Q3. So necessarily you're going to get the same thing if you do S2 times Q1 times Q3 or S3 times Q1 times Q2. So this is kind of an interesting quantity. We'll see that it has a major role to play in trigonometry of three-dimensional space. It's going to be leading to our notion of solid spread once we go a little bit further in the subject. I'll just flag for now that it's very important to realize that these three quantities are the same, and we have a very nice expression for that quantity in terms of a determinant divided by V11, V22, V33. This determinant D was the determinant of the matrix V. I'll just remark that the matrix V, since it's A times A transpose, its determinant is the square of the determinant of A. So we could also write this as the determinant of A squared divided by the product of the quadrances of the three sides of that so tetrahedron. That's a formula that we've seen before. So we've established the spread law with a minimal amount of fuss, just from the simple form of these quadrances and spreads. All right, so what about the cross law? That seems a lot more intimidating. But let's not be afraid of it. Let's have a good look at the cross law. Here it is again. S1, Q2, Q3 minus Q1 minus Q2 minus Q3 plus 2 all squared should be equal to 4 times 1 minus Q1, 1 minus Q2, 1 minus Q3. How are we going to prove that? Well, let's have a look at the left-hand side, and then let's have a look at the right-hand side. So the left-hand side has, first of all, this S1, Q2, Q3 in it. That's exactly what we've just been talking about. And we've just established that that's equal to D, which is the determinant of V, over V11, V22, V33. Okay, and then we're supposed to subtract these three quadrances. And here they are again. I'm writing them now as 1 minus V23 squared over V22, V33, and similarly for these ones. And then there's a curious plus 2 left over. All right, so let's have a look at that. Well, first of all, there's a minus 1, a minus 1, a minus 1, and a plus 2 for a total of minus 1 for the numbers. The whole thing is squared, and we're going to take this common factor V11, V22, V33 squared out from the square. So basically we're going to just get a common denominator for the whole thing and then take that common denominator squared out. When we do that, there will be a d left over here. What happens to this term here? Well, to get it over a common denominator of this, we need to multiply top and bottom by v11. So there it is there, and there's a plus sign because two negatives make a plus. So plus v11 times v23 squared over that same common denominator. Similarly, plus v22 times v13 squared, and similarly plus v33 times v12 squared. And then what about this thing here? Well, we had a total of a minus 1 left over from all these 1's and that 2. So when we get that minus 1 over a common denominator, we have to introduce a minus v11, v22, v33. So the left-hand side of the expression has this thing squared, and then inside the bracket is this expression involving d, and then this combination and this triple product here. Now let's have a look at the right-hand side. Well, that's actually sort of simpler because 1 minus q1 has a particularly simple form. That's just v23 squared over v22 v33. Remember, here was q1, so 1 minus q1 will just be this part of it. So there it is right there. So we get 4 times this, times this, times this. We see we get the same common denominator that we got over here, v11, v22, v33 squared. And then this thing over here is a perfect square. It's 2 times this product v12, v13, v23, all squared. Okay, so that's looking pretty nice. The left-hand side is a perfect square. The right-hand side is a perfect square. They have the same common denominator there, so we can basically ignore that. So it really amounts to showing that what's inside this bracket here equals what's inside this bracket here. Well, we're going to have to come to grips with D. What was D? D was the determinant of the matrix V. There's the matrix V again in terms of all the dot products. It's a symmetric matrix. Here is its determinant. So you need to be able to calculate a 3 by 3 determinant. Good exercise to calculate that determinant and convince yourself that it is actually 2 times v12, v13, v23 minus v11, v23 squared minus v22, v13 squared minus v33, v12 squared plus the product v11, v22, v33. That's the determinant of V. Well, so that means if we take this D and we add this and add this and add this and subtract this, what we'll be left with is exactly 2 v12, v13, 23, which is exactly this. So yes, indeed, just from what the determinant is, it's clear that what's inside this bracket here equals what's inside this bracket here. And so, since the denominators also agree, the left-hand side really is the same as the right-hand side, and that's the proof of the cross law. For sure, one of the most important formulas in geometry and indeed of all of mathematics. An elementary but interesting consequence of some basic playing around with 3 by 3 matrices, gram matrices, determinants. And finally, the dual cross law, which is just obtained by interchanging the Q's and the S's in the cross law. Well, that's an obvious consequence of the cross law because of the obvious symmetry between the elliptic triangle and its polar. Interchanging those triangles just means interchanging quadrances and spreads. So that's a very simple derivation of these important foundational laws for elliptic and therefore spherical trigonometry. A subject that, of course, has its roots in ancient history, a subject of great interest to the ancient Greeks, to the Arabs, to the Hindus, to all ancient peoples with the connection to astronomy and the celestial sphere. And the classical development of spherical trigonometry really continued into the 16th, 17th, 18th centuries. What we're doing is sort of at one stroke here, replacing that whole history and that whole rich body of formulas with alternate new ones. Okay? And these formulas are superior. They really are. And you learn something about mathematics. You learn quite a lot about mathematics and about geometry when you sit down with these formulas and study them a little while. Many consequences. We're going to see quite a few consequences for them here in this course. We talk a bit more about spherical trigonometry, lots of applications. So as a first illustration of the power of these formulas, let's derive some secondary sort of special cases, auxiliary results from them, very simply. So the first is Thales' theorem, that if you have an elliptic triangle where one of the spreads is 1. Now spread being 1 is the same as these two sides being perpendicular. In that case, there is an elegant expression of the other two spreads in terms of ratios or quotients of quadrances. So if S1 is 1, then S2 equals Q2 over Q1. So this spread here is the ratio of the opposite quadrants over hypotenuse quadrants. And similarly, S3, this one here, is opposite quadrants Q3 divided by hypotenuse quadrants Q1. And it's an immediate consequence of the spread law. Here it is there. So if S1 is 1, well then obviously S2 equals Q2 over Q1 and S3 equals Q3 over Q1. And conversely, if S2 equals Q2 over Q1, well then S1 has to equal 1 and so on. The next one, Pythagoras' theorem in this elliptic context. Also somewhat remarkable that these things are being written down, sort of for the first time really. Okay, what does it say? It says that if S1 equals 1, so exactly the same kind of situation, then there's a relationship between the three quadrances. And it's very similar to the rational Pythagoras' theorem that you learn in rational trigonometry in the affine setting. And I remind you that that is that Q1, it would be a capital Q1, is Q2 plus Q3. That's the affine, familiar Euclidean version of Pythagoras' theorem. Here the relationship is a little bit more complicated, but not too much and very elegant. It's that Q1, hypotenuse, is Q2 plus Q3 minus the product of Q2 and Q3. Of course, those of you who have been watching this course already will have seen this many times because we've already used the hyperbolic versions of this. But this is equally true in the spherical case. And how do we prove it? Well, from the dual cross law right up here, what happens if S1 is 1? Well, then the right-hand side is instantly 0. And we can also use Thales' theorem to have a look at what's inside the brackets here, to rewrite it. So the S2, we'll write it as Q2 over Q1. The S3 is Q3 over Q1. And the S1 is 1. There's S2 again, and there's S3, a plus 2. Well, that's got to be equal to 0 if S1 is 1. And then we look at this relation and say, well, okay, there's a bit of canceling with the Q1s there. So then we can multiply through by Q1, and we would get Q2, Q3 minus Q1, a plus 2Q1 for a total of plus Q1, minus Q2 minus Q3 equals 0. We get this relationship here. And then if you bring these ones to the other side, you get Q1 equals Q2 plus Q3 minus Q2, Q3. So it's a pleasant consequence of the cross law, or the dual cross law in this case. This formula is very rich, okay? Very, very beautiful formula. Of course, there's a dual result to Pythagoras' theorem. The dual Pythagoras' theorem says that if little q1 is 1, then S1 equals S2 plus S3 minus S2 times S3. And of course, it just follows by the duality between quadrants and spreads. Here it is here. So this is a little bit of a novel interpretation. Q1 equals 1. It means that these two elliptic points have quadrants of 1. What does that mean? Well, it means that if you look at the corresponding lines emanating from the origin, they are perpendicular. So that would mean that on the sphere, you'd have situations, say, like this one and this one. The corresponding lines to the origin are perpendicular. So that's a quadrants of 1. And then we have the triple quad formula, which is another special case. It's sort of a degenerate case. What happens when one of the spreads collapses to 0? Well, then the other ones, in fact, do as well. But then the relation is that there's a relationship between just 3 quadrants is formed by 3 collinear points. So the collapsed triangle, we have A1, A2, A3, all collinear, so that means their corresponding one-dimensional subspaces are all on a plane. And we have quadrants as Q1, Q2, and Q3, and we want to know what the relationship is. And here's the relation. It's the same relation as what we say in rational trigonometry is the triple spread formula. Okay, but here it's the triple quad formula. Q1 plus Q2 plus Q3 squared equals 2 Q1 squared plus Q2 squared plus Q3 squared plus 4 Q1, Q2, Q3. All right, so the proof. Well, if S1 equals 0, then in the cross law, you just plug in S1 equals 0 and it simplifies. So the left-hand side becomes 2 minus Q1 minus Q2 minus Q3 squared equals 4. 1 minus Q1, 1 minus Q2, 1 minus Q3. All right, we can expand that out. So think of this as 2 minus Q1 plus Q2 plus Q3 all together. So the square of the first term, square of the second term, minus twice the product. And then we just expand this out. We get 4 minus 4 Q1 plus Q2 plus Q3. So you expand this thing out, there will be a Q1 appearing, there and there and there and so on. There will be some quadratic terms, 4 with Q1, Q2, plus Q2, Q3, plus Q1, Q3, with the plus sign. And then there will be the 3 cubic terms, minus 4 Q1, Q2, Q3. Okay, so that's a consequence of the cross law, and S1 equals 0. And now we see that there's a bit of cancellation. The 4's will cancel. This term here and this term here will cancel. We could bring this thing here to the left-hand side, so 4Q1, Q2, Q3, and bring this thing to the other side, so with a minus sign, and we still have this thing left over. So what happens when you expand this thing out? Well, you can get minus Q1 squared, minus Q2 squared, minus Q3 squared, and then minus twice the various products, so giving altogether twice the various products. And then, if you think about it, you can rearrange that as just positive Q1 plus Q2 plus Q3 squared minus twice Q1 squared plus Q2 squared plus Q3 squared. So when you expand this out, you're going to get twice all the products. That's the same thing that you had over there. And the Q1 squared, Q2, Q3 squared here will cancel with the minus 2 to give you minus Q1 squared, minus Q2 squared, minus Q3 squared coming from here. So just a little bit of algebra, it goes from here to here, and then that's essentially this form of the triple quad formula. And of course there are other ways of writing it too. That's sort of my preferred form. Alright, so we've done very well. Okay, we've established these very important formulas that gives us a lot of power. It essentially opens up a whole new chapter in our understanding of three-dimensional space. So many doors are now open that we can work with things algebraically. We can throw our calculators away, or at least only use them to simplify big calculations. They're no longer essential because we don't have to deal with transcendental quantities. We don't have to deal with the circular functions. We can just work with these algebraic laws to derive all kinds of things and to really reveal structure that has been hidden for a long time. Very exciting and lots of possibilities. Also possibilities for amateurs to make new discoveries. Of course, there are a whole raft of secondary formulas that we could establish from these ones, but these are the main ones that you want to know. Okay. So next time we're going to have a look at some applications of these laws that exhibit how pleasant they are and how explicit we can make calculations. The litmus test of a good theory. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.